Hello students, in this video we'll introduce the gradient vector for a scalar function. If we're given a function z equals f of x, y, then we define its gradient vector field more specifically, it's Euclidean because this is the representation of the gradient vector field that only holds in Euclidean or Cartesian coordinates by gradient of f is going to be a function. It's going to be a vector field. It's going to be partial f partial x, which is a function of x and y in the direction of I hat, plus partial f partial y in the direction of j hat. In other notations for this, sometimes you'll see this notation in an upside down triangle. F is the same thing as the gradient of f. And so what happens over here is the gradient of f inputs an x and a y, and outputs an I and a j. So it's a mapping from R2 to R2, and it's a vector field. You input a vector and you output a vector, so it's a vector field. We can also extend the definition of gradient to functions of three variables. If, for example, we had w, which was f of x, y, and z, then we would define the gradient of f, or the gradient of w, because f and w are the same, to be partial f partial x I hat plus partial f partial y j hat plus partial f partial z k hat. And this upside down triangle of f is a mapping from a three-dimensional vector to a three-dimensional vector. And again, it's a vector field. We'd say that this vector over here is a two-dimensional vector field, and this is clearly a three-dimensional vector field. So we can easily compute examples of gradients. So for example, let's just do a calculational example. If we had this function over here, if I had z was equal to x squared plus y squared plus an x sine of x times y, then what would the gradient of z be? The gradient of z will be the x partial derivative, which would be a 2x, and then we'll have a sine of xy, then a xy cosine of xy I hat, and then we'll do the y derivative, so we'll have a plus 2y, and then we'll have a plus x squared cosine xy j hat. And that is our gradient vector field for this variable z. Now, there is we should make some notes about gradients, so some properties of gradients. So properties. If we want to compute the gradient of a multiple of f, that is just that multiple times the gradient of f. If we wish to compute the gradient of f plus g, that is the gradient of f plus the gradient of g. If we wish to compute the gradient of the product of f and g, that will be f gradient of g plus g gradient of f. That's the product rule for the gradients. And we'll see in future videos that this will be important. So if gradient of f at a point x, y was the zero vector, this implies that the point x, y is a critical point of f. And critical points we'll see can be one of three things. These critical points can be local mins, like in Calc 1, local max, like in Calc 1, but there's a slight variation in Calc 3. They can also be local saddle points. So in future videos, we'll discuss how critical points interact with the gradient and how we can classify critical points are local maxes, local mins, or saddles. Thank you very much.